Hi guys, and welcome to the dyno room. Today we're talking volumetric efficiency. Now I know Matt's already done a video on volumetric efficiency. He's explained the ins and outs of how the software works and how we calculate everything in the background. Today I'm going to be using that theory, putting into practice with this RA23 Celica. Now before we lift the hood on this car, I really would recommend you to jump over and have a look at Matt's video on volumetric efficiency tuning. That's kind of the part one to this practical video. So Matty's done all of the theory of exactly how volumetric efficiency tuning works in the background in the engine management system. Even if you know everything there is to know about volumetric efficiency, jump back over there for a recap. There might be something you've missed or something that sort of clicks and you think, oh, that's why we need injector size or air temperature or engine size. Go over there, have a look at that, then we'll get straight into this. And this is an RA23 Toyota Celica, but because it's here, it obviously doesn't have the factory engine in it. Let's crack it open, take a look. Under the hood here, she's absolutely beautifully presented. They put a lot of time and effort into color coding everything, making it all sort of flow and fitting this Toyota. This is a Nissan SR20 turbo engine. Somebody's obviously got a sense of humor. Going with the all black theme, it's got a powder coated Plasma Man intake manifold mated to a Bosch 74mm throttle body, plasma clamps, so it doesn't actually have silicon hose joiners attaching the intercooler piping to the throttle body or to the turbocharger. Instead, it's got these clamps that click everything together for ultra high boost applications. Black intercooler pipes, a black Plasma Man intercooler along the front, and a really, really nice black radiator just behind it that fits so beautifully well in the grille here. On the hot side there, we've got a Garrett GT35 base turbocharger. Front cover's black, the rear housing is black, all of the airbox part and the intake pipe is black, the breather's black. It looks really, really nice. The Turbo Smart fuel pressure regulator is even black. It looks really, really nice in here. Electronics-wise, the part that I'm always interested in, it's got the Nissan R35 coil conversion, which is getting super popular now for all Nissan, pretty much every brand of engines. They've been performing really, really well, allow huge cylinder pressures with no misfires. Readily available, reasonably priced, can't beat them, really good thing. We've got a Haltech wideband controller on the car, one of our WB1s. It's got the oxygen sensor down here in the dump pipe. We've got a set of Bosch 2000cc injectors, air temp, oil pressure, fuel pressure sensors. We've got a crank trigger kit on the front of the engine, so it's actually got 12 teeth on the crankshaft and a single tooth on the camshaft, meaning that we don't need to use the factory Nissan crank angle sensor. That's the one that sits up the top normally. Other than that, it's a Nissan SR20. It's going to make good power. We better get inside and get on with what we're actually talking about today, volumetric efficiency. This car's running our Elite 2500 series ECU, meaning that the base fuel table can be tuned using the volumetric efficiency method. The method that I absolutely love, I recommend to everybody, well over the old style injection time tuning method. So let's talk about that just a little bit. Back before we had volumetric efficiency tuning, we used to tune our base fuel table in what we used to call injection time. And what that means is that in our base fuel table, this one just here, I'll click around in there a little bit. What that means is that on the left-hand side here, we've got our engine RPM axes. Along the top, we've got our load axes. So in this particular car, our load axis is manifold pressure along the top, engine RPM down the side. In the old days, if we went to, just here, 2 pounds of boost, 4,500 RPM, instead of seeing a volumetric efficiency number there, we used to see just an injection time. It might have been 3 milliseconds, 4.5 milliseconds, 6 milliseconds. It all depended on the size of the injectors that you had and the engine combo you had. So it wasn't really a uniform way of tuning an engine. It was a lot more complicated. There were a lot more numbers to enter. Things weren't as linear at all. Temperatures weren't taken into consideration, so we needed to really focus on our fuel air temp compensation tables. Overall, it was just a way more complicated way to do things. Fast forward into the future, Our VE tuning models have made everything so much easier. They've made cars drive smoother, better throttle response, better fuel economy, and faster tuning, meaning that you get off the dyno faster. You're not wearing the engine while you're sitting on the dyno tuning every single load cell. You can linearize between load cells and still get a really, really great result. So let's take a look at how it works on the dyno. Remember, before we get to any of this part, you really should have checked Matt's video, episode 1 of the VE tuning videos. Once you've seen that, this will be a breeze. Before we even start the engine, there's a couple of things that we need to fill in order to give our VE model all the information it needs in order to determine how much air and how much fuel is going into the engine every time that camshaft spins around. So if we go into the main setup, first thing we need to look at, engine, main, engine capacity. This is an SR20, it's a 2-litre engine, so I've got here 2000 cc or 2 litres. That means that every time that camshaft spins around, that crankshaft will spin around 2 times because it's a 4-stroke engine. It'll move 2 litres of air from the intake out into the exhaust if it was 100% efficient. So, engine capacity, that's pretty important. We need to make sure we've got a manifold pressure sensor that's connected to the intake manifold that's between the throttle butterfly and the intake valve. I've got one of them set up. At the moment, it's just reading no boost, no vacuum. We're just sitting here in 1,013 millibars of barometric pressure. The next critical sensor is our inlet air temperature sensor. So this sensor is normally mounted in the intake stream, somewhere where it's not going to get heat soaked. So you don't want it in the back of the inlet manifold. Typically somewhere a few inches just before the throttle body is ideal, where you're going to get the most airspeed. Now we need a working intake air temperature sensor because we need to measure how hot that incoming air is. Reason being, the hotter the air is, the less oxygenated that air is, meaning that we're going to have to change our VE model depending on how hot or cold the intake temperature is. The colder that air gets, the more fuel we're going to need. And lastly, on our VE critical sensors, the engine RPM sensors, the trigger signal, the one that tells us how many RPM, how many revolutions per minute this SR20 engine is doing. I need to know how many revolutions it's doing in order to determine how much air should be pumping through that engine. With the combination of these sensors all going into the ECU, it can now calculate the mass of air that's going through this engine when it's at 100% efficiency. So if I come down here to my base fuel table, which I've already put some numbers in this and I've already sort of roughed a tune into it, if we were at 100% efficiency, which up here somewhere at 7,000 and 8,000 RPM, that means that 2 litres is coming through, 2 litres is leaving. Keep in mind, and like Matt was speaking about, if we're adding 15 pounds of boost into this engine, we don't call that 200% efficient. We still bring that into our VE calculation with our manifold pressure sensor. So we are talking about a rough VE at idle of around 50% for a 4-stroke engine, and a rough VE flat out full power at around 90 to 100% for a super high performance engine. But I keep talking about 100% efficient. Yeah, I know we talk about Formula One cars being over 100% efficient. I know that we talk about old V8 farm equipment being not very efficient. Look, the idea of it is that most 4-strokes, and I'm sort of speaking generally, around 50% at idle and around 100% flat out. This is one of the great things about VE tuning, is that if you know that, you can rough a map in, and with a bit more of the magic that we're about to talk about, hit the key, the thing will start, run, cruise, drive, and then we can rely on the O2 control to get us in the ballpark so that anyone can tune a fuel map. But what is the fuel map? Well, that's what I've got open right here in front of me. So if you flick down to the screen, this is what I was speaking about, where I've got our load reference, our fuel load reference, or our manifold pressure across the top of the screen here, and our engine RPM up and down the side. If I come to a position here at, let's say, 3,500 RPM, 0 vacuum. So that means we're not in vacuum and we're not in boost. 76.3 is the number that's there. What that's telling me is that I believe that this engine will fill the cylinder 76.3% of 2 litres of air. That's how efficient it will be. If I thought this thing was absolutely amazing and it's a Formula One car and everything is perfect and it's the best engine ever made, I'll put 100, everywhere. Ideally, if you could make a 4-stroke engine that was 100% efficient absolutely everywhere, you'd be pretty rich. That would be ideal. It's probably not going to happen, at least in my lifetime, I would imagine. So you get the idea that all I need to do here is type in how efficiently we're filling this engine, or how efficiently the engine is filling itself, basically, with its camshaft, its engine design. So what's happening here is at idle, and down here we might be idling at about 20 inches of vacuum and at about 1,000 RPM. I'm saying this thing's about 44% efficient. It's got a fairly large set of camshafts into it, so typically with that, at idle and light load, you'll actually end up with a lower efficiency when you've got a big set of cams, where it'll become more efficient as we start revving it. Likewise, if it had a factory set of camshafts, I'd expect it to pick up a little bit of efficiency at idle. But again, these are all just the numbers. So what this is telling us here, 50-ish% at idle, 100% flat out, that's what we need to talk about. But so far, all we've talked about is the air going into the engine. It's only one part of it, right? 14.1, or air to fuel ratio. So air is the part that we've talked about. Now, let's talk about the fueling. If I want to know about my air to fuel ratio, right now, I know how much air is going into the engine, 2 litres. If we know, we go through all the mass and figure it all out, then we get to the mass, or the weight of the air that went into the engine. Now, I need to mix that air with fuel in order to put that 14.7 to 1, or whatever air to fuel ratio you want. I need to be able to put them together based on mass. So I know the mass of air coming into the engine. Let's figure out now the mass of fuel that's coming into the engine. So if I come down here to my injection system, my injector flow rate. This engine's got a set of the Bosch 2000cc injectors in it. This here is what I've calculated out as the injector flow rate based on the differential injector fuel pressure. So what that means is the pressure across the injector. So if we've got, say for example, 58 pounds of fuel pressure up the back of the injector, but then what if we've got 10 pounds of boost operating on the other side of the injector, or forcing on the other side of the injector? That would be 58 minus 10, 48. That means that injector has a differential fuel pressure of 48 psi, and that 48 psi is the amount of flow, or the amount of fluid that will be able to go through that injector. So that's the reason why we need to map our injector flow rate versus our injector differential fuel pressure, because our injectors are actually changing our flow depending on how much pressure is on the fuel pressure line itself and the manifold pressure. Ideally, it's the job of the fuel pressure regulator in order to bump up our fuel line pressure when our boost pressure comes up. In a perfect world, that means that the flow across the injector would always be perfect. But we know that's not always the case. And we know that because there's diaphragms, there's lines, there's pumps, there's all these things involved that are acting on that. So it's always best to map against injector pressure differential in order to get the most accurate fueling. So we know how much fuel is going to pass through our injector at all of these different pressures. There's one really important thing here as well. It's all over the internet. Everyone loves to talk about it. It's called injector dead time. I'll click down on this table here. All right. To understand that, we first have to realize that the injector is a little electronic solenoid. When we apply power to that injector, the little valve inside opens and runs a path for the fuel to get down through the valve, out to the other side, into the engine, and fuel our dreams. But it would be foolish for me to think that as soon as I apply power to that injector, it's giving us 100% of its available flow. That's not the case. When we energize that solenoid, it takes a little bit of time for that pintle to open and for fuel to start flowing. That's what's known as our injector dead time. So why is injector dead time so important? Well, it's important because I need to know how long it takes for the injector to physically open and start spraying fuel at its advertised flow rate. If I just assume that it operates at 100% efficiency as soon as the injector driver opens, well, I'd be wrong, and my air to fuel ratios would be all over the place. Now, let me give you an example of that. Let's just say that our injector dead time is 1 millisecond. So like a lot of injectors are all different. They're somewhere between a half a millisecond to 1.5 milliseconds. It's dependent on battery voltage and it's dependent on differential fuel pressure. Now, let's just say, for example, at idle, our injector dead time is 1 millisecond. Okay, that's a millisecond there, about that. At idle, this engine might be idling with our Bosch 2000cc injectors at, let's say, 3 milliseconds of total injection time. Let's say that's there. Now, what that means is that 1/3 of that injector pulse is dead, gone to injector dead time, whereas 2/3 of it is spraying fuel into the engine. Now, percentage-wise, 33.3% of that injection pulse is gone. What happens then later, if I'm trying to feed 10 milliseconds of injection time into this engine, for example, that percentage changes a whole lot. And that's the reason why injector dead time, while it's critical across the whole operating range of the engine, you're going to notice more problems with injector dead time at light load, idle, and cruise conditions. So now we know at 100% efficiency, this engine is going to move 2 litres of air from one side to the other. Because of the temperature sensors, we're going to know the mass of the air. Because of the dead time, we know how long the injector takes to open. When it starts flowing, because of the flow table, we know how much fuel is going through the injector. Now, we just need to tell the engine management system what is flowing through the injector. If I come to the main setup here, into fuel, the fuel type, we need to tell the engine management system, is this thing running petrol? Is it running ethanol? Is it running methanol? Because all of those fuels have a different volume by weight. Likewise, we also need to tell the engine management system the density of that fuel. Now, that density is how many kilograms for a cubic meter of that fuel. The E83 fuel we're using has an advertised fuel density of 737.2 kilograms per meter cubed. So meter by a meter by a meter, fill it up with fuel all the way to the top, it's going to weigh 737 kilograms. If we were filling that same cube with water, it would weigh 1,000 kilograms or 1 ton. This means that fuel is lighter than water. And that's it. That's everything we're going to need. That means that we know exactly how much fuel is flowing through that injector. We know all about the mass of the air. The air to fuel ratio, we're ready to rock and roll. So the last thing is we need to set our target air to fuel ratio map. We come up to here, lambda target. All right, if we have a look in this table, I've got this table set up as petrol AFR. I find that the easiest to tune it. I personally like that. Some people can tune in lambda or in their ethanol numbers. Personally, these are the numbers that I use. If we come across here, what this map is telling me is that right here, I would like to mix in 14.4 parts of air to 1 part fuel. So this engine at 0 atmosphere, so no boost, no vacuum. If this was an aspirated engine, that would be wide open throttle at 2,500 RPM on our E83 fuel. I'm going to run 14.4 parts of air to 1 part fuel. Likewise, up here at 20 pounds of boost pressure and 8,000 RPM, I'm going to run 11.4 parts of air to 1 part fuel, our air to fuel ratio table. Now, there is a lot of confusion about this table because it actually has 2 functions. Our first function is for it to command the air to fuel ratio for our VE modeling. Its second function is used with our O2 sensor. It just so happens that it's exactly the same table. So what's going on here is when we turn our O2 control on, our air fuel ratio sensor that's mounted in the exhaust system will measure said air to fuel ratio. If I've messed up my base VE numbers, if I've messed up my dead times, if I've messed up my injector flow, my air temperature's in the wrong spot, my engine size is wrong, we're not going to get the air to fuel ratio that I've desired here. The oxygen sensor is going to pick that up. It's going to show me an air fuel ratio error. Then it's going to make a percentage change in order to try and meet this target AFR table. So for our practical example today, I'm going to disable our O2 controller in the engine management system. The sensor will still be there, so we'll still be measuring the air to fuel ratio, but there'll be no reactive feedback. So what that means is there's going to be no percentage corrections in order to achieve these target tables. We're going to be relying on the VE model only in order to achieve these targets. So we're on our mainline dyno here, and what I'm going to be doing, I'm going to cruise the car up. She's up to operating temperature. I'm going to cruise into 4th gear. I'm going to hold it at about 40 kilometers an hour, so a fairly low sort of, and it's about sort of 1500 RPM. So what we can see here, if we look at the screen, our target lambda is 14.3. Our actual lambda is 14.3, 14.4. Now, remembering this thing's got 2000 cc injectors in it, so that's pretty good. The smaller the injector, the closer to the target you're going to be able to get all the time. When we're talking about a 2000 cc injector on a 2-litre engine, we really do start to see little control issues there with really, really low injector pulse widths. So just keep that in mind. But look here, we've got a target of 14.3, an actual of 14.3. That means that my VE number there is probably about right. Our O2 correction is disabled. So I'm just going to show you here in the software, disabled. If I go up to my target AFR table now, watch what's going to happen here. Instead of me wanting to go to, say, 14.3 there, I'm just going to type in 12. 1, 2, 3, enter. Look at that. No O2 correction. Wanted 12, I've got 12. 13. Enter. Target's 13, actual 13. I'll go Control Z, undo, Control Z, undo. Back to my target of 14.4, and it's 14.4. There we go. So what that's telling me is that my volumetric efficiency at this particular position in the map is tuned correctly. So what if we go and try and stuff some stuff up here? Let's come down to our injector flow rate. What if I tell the ECU something that's wrong here? I'm going to highlight that, and I'm going to go, it's out by 10%. 10, make the injector 10% bigger than it actually is. Enter. Oh, it started to go a little bit lean here. So now the engine's running at 15.7 to 1 instead of my target of 14.3. That's because the ECU just reduced the injector pulse width because it thinks more fuel is going through that fuel injector than it actually is. Control Z to undo that change. Now, let's say that it's got a really small injector in it. I might go minus 20%, for example. So instead of the injector operating at 1851 cc's at the moment, it's now operating, assuming it's a 1480 cc injector. And look what's just happened. Now the air fuel ratio is 11.3 or 11.4 instead of my target of 14.3. I'll undo that change. It'll come back to my target. Things are good. What if I move my dead time around? So instead of me having a dead time right now of 1.17 milliseconds, if I highlight the whole lot, P for percentage, I'm going to go a bit crazy and go 100% bigger. 2.2. Oh, you could hear the engine note change. You went to 9 to 1. I'm going to undo that change pretty quickly and bring it straight back up. What I might do instead of making such a large change, which you can see how much that affected the engine, it even started pulling it down. Now I'll go page up, page up, page up. We're not meeting our target anymore. Control Z to undo that change. Page down, page down, page down. So now I'm telling it that the injector is actually flowing fuel faster than it really is. All of a sudden, it's showing that I'm running lean. Undo. Back to our target of 14.4. Give it some revs, make sure she's happy. Beautiful. I'll turn this off so we can hear a little bit better. So now with that practical example, you can see that making changes to these critical inputs directly changes the air to fuel ratio that the engine's going to be running. and we no longer meet our targets. This creates a really big problem when we start to tune the engine, because when I want a specific target air to fuel ratio, I don't want to be mucking around trying to manipulate the maps because I've put the flow rate in wrong, or I've put the dead time in wrong, or I've put the engine size in wrong. So we need to make sure that the things we've spoken about today are entered correctly in order to make sure the tuning process goes as smoothly as possible. Now, the one thing that we didn't just do then is start it up and adjust our VE numbers in the base fuel map. So I'll do that now and show you what happens when I adjust the base VE numbers. Just like everything else, still we affect the fueling in exactly the same way. We're no longer going to meet our target. So the whole purpose of that base VE table is to go through and tune as many of those cells as possible in order to make your target lambda table meet your actual lambda. Okay, we're straight back up to that RPM. And after our post-start correction starts, so post-start being after the engine just initially starts, we add a little bit of extra fuel to help it to get running. So we're right on our target here. I'm just going to highlight all those fuel cells and I'm going to go up, 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 up. We're putting more fuel into the engine. So this is one way that you could tune the engine. You could ignore the target AFR table. You could put random numbers in here in order to achieve the air to fuel ratio you want on the dyno. But you're going to paint yourself into a corner if you try and do it this way. It's a misunderstanding of how the volumetric efficiency system works. And where you run into problems here is if all of a sudden you want to choose a different air to fuel ratio, or if you want to change your injectors, you don't have to retune the whole map. All you have to do is dial in your new set of injectors. So it's best to do it right the first time. Now, the last thing that I want to do is turn on our O2 control function and show you that that's working separate to the VE model. I'm going to pop up here to the main setup. I'm going to flick our O2 control on, press apply, control F12 to reset the ECU. Okay, you'll notice this page came back just then. Short-term fuel trim. So this is telling me how far out the base VE table is. Okay, I'm going to go back to exactly the same load side on the dyno. And here we go. So right now, the short-term fuel trim, minus 1%, say give or take. So that means that my base VE table is out by 1% in order to achieve my target. Now, there's no shame in relying on the O2 controller to do a little bit of the tuning work for you. And the reason why is you simply can't tune the engine across all of the engine operating conditions, all the different temperatures, all of the different cranking and post-start tables. So letting the O2 controller do some of the work around idle and cruising, and realistically, personally, I use the O2 controller on over wide open throttle conditions because I always want that O2 controller doing as much work as possible in order to get the best driving engine, to get the most efficient tune, basically to get the best fuel economy. I use the O2 sensor in order to set up my engine protection, so if anything does go pear-shaped and the thing does lean out for whatever reason, it's going to shut down before we can do real engine damage. The reason why I wanted to turn the O2 controller on was to have a bit of a look here and show you what happens here. Now, if I mess up this VE map by, let's say, P for percentage, I'm going to add 5% fuel to it, meaning that it should go 5% richer than it is. Enter. Watch what happens. Yeah, it did go rich for a second, but then have a look at that. The short-term trim immediately pulled that fuel out. We're back to our target, and all that's just happened is now our short-term fuel trim is working harder. I'm going to undo that change, Control Z. It goes lean for a split second. The O2 controller sees it, goes back to what we had originally. Let me pull some fuel out of the tune. I'm going to pull out, let's say, P for percentage, minus 10. You'll notice I like using percentages a lot more than pressing page up and page down. I use percentages because it keeps the shape of the map, and that's what I like. So let's pull out 10%. 1, 2, 3, enter. Oh, I felt that on the dyno, and it just went to 15.6 for a split second. Then we're straight back to our target. And Look at our short-term fuel trim. It's now adding 10%. So knowing what you know from seeing this, you'll see how I'm actually tuning this car. What I typically do is go through cell by cell. I leave the short-term O2 trim turned on, and I'll go through and look at how much the O2 controller is doing, how much work it's doing. That way, I don't have to do any maths in my head. What I'm gonna do here is go peep a percentage, add 5% to these particular cells. If I was tuning it, you know what, 5% is probably not enough, because the truth is, if it was only 5% too rich, I would probably leave it at 4 or 5%. So let me go. I'm gonna undo that change. Okay, let's go for something a bit bigger. Let's go for 10%. So now my short-term fuel trim is sitting there at 8%. So imagine I had just started doing my sweeps through this run. I'm at 1500 RPM. I'm at 23 to 24% throttle, and I'm at 0 vacuum or 1 pound of boost pressure. It's 10% too rich. I could look at the numbers and think, oh, okay, it's 10% too rich. I'll divide this by this. Or if I was in Lambda, I'd say, oh, okay, I'm at 0.98. I want to get to 0.96. That divided by that is or minus that, I should say, is 0.02. So that's a percentage change I'll make. Why not just use the O2 controller? You'd look at this and say, all right, I'm 9.5, 10% out. P for percentage, -10. Watch the short-term trim. Look at that, we've got no trims. Our target is meeting our actual. The VE is right there. Move to the next cell and she's away. And that's how it's done. And I know I've only sort of focused on one cell here. I've done that so we can see how repeatable it is on exactly the same cell. If we were tuning this car, we'd be going through row by row. We would lock the dyno at 1500 RPM. I'd use the throttle to manipulate the manifold pressure to run across every cell that I can possibly get on our mainline dyno. Then I'd let out more road speed and I'd come up to a higher RPM, so 2000 RPM, and I'd do as many load cells as I can get to. That's what's known as steady state dyno tuning. As soon as I got up to a point high enough where I felt a bit uncomfortable, we're loading the engine's making a bit of heat, from there I would move away from doing steady state tuning and I'd start doing power runs. The beauty of all of this stuff, coming back to it, is that if you put in the work early on, if you set everything up right, if you put the right data in down low, if you set your desired target air to fuel ratios, as soon as you start going in the power runs, odds are you'll be able to guess the shape of that table. The first power run, it's going to hold a dead flat air to fuel ratio because your guess is going to be pretty close. Then your short-term fuel trim on your O2 controller is going to take up for any little errors or just anything that you weren't quite sure about. Then after that first power run, you can see your short-term fuel trim. You can see what the engine management system was doing in order for your desired and target air fuel ratios to match. Then you can apply that short-term trim to your base VE table and you're a tuner. And there you have it. So that's a practical example of how the VE model works on our engine management system. Now, if you really want to be a tuner, getting the fuel map is absolutely critical in getting a car to cruise, idle, start nice, as well as keeping the engine alive under full power. So doing this and practicing this over and over again is the best way to get a better understanding of how your engine management system works. I remember when I first started tuning VE-based engines and engine management systems, the hardest part for me to get my head around was that the air around us has a mass. And I'm mixing that mass of air with the mass of fuel that we're putting into the engine against my target air to fuel ratio table. So get your head around that. The air around you has mass. As always, I know it's been a really long one, but thanks so much for watching. My name's Scott. Catch you next time.